In the last class we had started on the simple harmonic oscillator problem, and I have shown you that for any time independent problem, the time part of the wave function is just an oscillating phase. For a stationary state, the time part just keeps on oscillating with some frequency, and it is the spatial part which we are now looking at for a simple harmonic oscillator. And we were trying to solve this eigenvalue equation where E is an unknown eigenvalue of the Hamiltonian of the simple harmonic oscillator. This equation was simplified by dividing it throughout by h cross omega and multiplying by 2, which allows us to scale x in terms of some length scale x naught, which is intrinsic to the problem, where x naught is square root of h cross by m omega, and we defined a xi which is x by x naught and wrote this same equation in terms of xi. So this equation written in terms of xi, as we saw in the last class, was this, the equation over here. Now in the last class we had called this quantity over here n. Let us not do that, because and then we found that it created some little bit of confusion. So let us not do that, we shall come to that a little later. So let us just take this equation, which is the same Schrodinger equation, just scaled using the scaled position x by x naught, which is xi. In this we make a substitution, we take a trial wave function which is of the form xi x is equal to psi xi is equal to some function of xi into e to the power minus xi square by 2. So we take a trial function of this kind and we plug this into this equation. So if we calculate the derivatives of xi, the derivative which occurs here is xi double prime, where prime indicates derivative with respect to x. So if we calculate xi double prime, which turns out to be this, then and we plug it in here into this equation, then what we find is as follows. We find that the xi double prime over here, this this term over here is just equal to xi psi. This term is xi square psi. So this term cancels out with this term, and what we have left are 1, 2, 3, and we have left this term over here. So let me write down the equation which remains after we make this substitution. So what remains, and the e to the power minus xi square by 2 also cancels out throughout, and what remains is minus v double prime plus 2 v prime into xi plus v is equal to 2e by h cross omega into v, which if you simplify, just bring this onto this side and multiply throughout by minus 1, what it gives us is v double prime minus 2v xi v prime xi plus 2e by h cross omega minus 1 into v is equal to 0. So this is the equation we want to study now, which is the same old equation, the Schrodinger equation, with the substitution that psi is equal to v into a Gaussian. Now here it is convenient to define this whole thing over here, which is a some number, to be n. So, let me write down the final equation which we would like to study in the next page. So, the equation which we want to study is V double prime minus 2 xi V prime plus, no, we call this 2n. So, let me just write down the whole thing here, 2e by h cross omega minus 1 is equal to 2n, or E is equal to h cross omega n plus half, where as of now we have no constraint on n could be any number minus infinity to infinity. Let us see if finally we end up with some constraint on n. So, we have two, going back to the equation, we have this. Now, we proceed to solve this equation by making a series expansion of the function v in terms of psi. So, we expand v in terms of psi, which gives, so we assume that v of psi is equal to summation over m equal to 0 to infinity Cm xi to the power m. So, with this we find that v prime is equal to summation m equal to 1 to infinity. If we just differentiate this, the derivative of the m equal to 0 term, which is a constant, is 0. So, that does not contribute, it starts from 1 and goes to infinity. We have Cm into m into xi to the power of m minus 1, and v double prime is equal to, now m will start from 2. So, we have Cm into m minus 1 into xi to the power of m minus 2. So, Cm into m into n minus 1 into xi to the power of m minus 2. So, we know what is v prime, what is v double prime. Now, if we calculate xi v prime, which is what we need here, this is equal to summation m equal to 0 to infinity Cm into m into xi to the power of m. The m equal to 0 term is 0, as we expect, because we get this by just multiplying this by one factor of m xi. So, we take these three, we take this, this and this, and substitute it into this equation. And what does that give us? Let us calculate that. So, what we obtain, I am writing down the result when I plug in all of this into this equation over here. So, the first term v double prime is equal to sum from m equal to 2 to infinity, I am not showing the infinity here, and then I have Cm and then I have into m minus 1 to the power of xi m minus 2. Now, if you look at xi into v prime and v, so xi into v prime is here and v, you will see that they all run from m equal to 0 to infinity, and they all have xi to the power of m when I have the index m over here. So, I can combine these two terms, I can take it to the right hand side and combine these two terms to obtain that this is equal to sum of over m equal to 0 to infinity, and I can combine these two. So, what I get is Cm, this will contribute 2 into m. So, I have 2 into m, and this will contribute minus 2 into n. xi to the power of m. So this equation gives us this equality between these two quantities. Now these two quantities should match for every power of xi. So if we equate the coefficients of some fixed power of xi, let us say we fix say s, let us take some power of xi, let us take some power s. So let us look at the coefficients of xi to the power of s. So if m is equal to s on the right hand side, then m minus 2 should be equal to s on the left hand side on this term. Here if m is equal to s, then here m should be equal to s plus 2. So the coefficient of the term, so s plus 2 should occur over here and s should occur over here. So the resulting equality between the coefficients which this gives us is as follows. So what we obtain is the relation that c s plus 2 into s plus 2 into s plus 1 is equal to cs into 2s minus n, where n is some constant which is a part of the equation. N follows from the energy, from the eigenvalue which we want to solve for, which gives us the so this is the recursion relation between the different coefficients c. Now so what does, let us write it in this fashion, cs plus 2 is equal to 2 into s minus n divided by s plus 1 s plus 2 cs. So this is the recursion relation. If we know one particular c, then we can work our way to find the coefficients of all the other exponents, of all the other powers of xi. Now let us study this in some detail. What are the features of this recursion relation? The first feature I want you to note is that suppose I start with C0. So I am starting with C0. If I start with C0, what this will give me is C2. So once I fix C0, the value of C2 is going to be determined by this. And then the value of C4 is going to be determined by this, and the value of C6, and the value of C8, etc. So we will have all the coefficients of all the even powers of xi. Now suppose we start with C1, then this is going to fix C3, which is going to fix C5, which is going to fix C7, and we will have all the odd powers. So this will give us the even powers, the coefficients of the even powers. This will give us the coefficients of the odd powers. So the coefficients of all the even powers are determined by C0. Once I fix C0, all the other coefficients can be determined. For the odd powers, once I fix C1, all the coefficients are determined. So I find that we have two independent series, one arising from C0 and the other one from C1. So there are two independent functions. So we can write the whole thing in the following way. We have one function V1 of xi, which we can write as 1 plus A2 xi square plus A4 xi 4, etc. So this is one function where we have chosen C0 to be 1. We could always multiply the whole thing by a number. And we have another function V2x, which is equal to xi plus A3 xi cube plus A5 xi to the power of 5 and etc., etc. And the general wave function psi, which is a function of xi, could be written as some coefficient a into v1 xi plus b into v2 xi, let me get rid of this, into e to the power minus xi square by 2. Now, if you look at v1, you will realize that v1 is an even function, in the sense that if I use minus xi instead of xi, I will get the same function. If you look at v2, it is an odd function. If I use minus xi instead of xi, I will get the same function with a minus sign outside. So this is an even function which has got all the even powers of xi. This is an odd function, and the odd function and the even function appear with two independent coefficients. So I can add up these two functions with two independent coefficients, multiplied by e to the power minus xi square by 2 to get the wave function psi. Now let us look at the behavior of these functions v1 and v2 as we go to large xi. For small values of xi, if we restrict ourselves to small values of xi, then only a few terms in the expansion will suffice, because the larger powers will fall off for small values of xi. But once the value of xi gets large, you have to look at the large powers, because they will be the ones which will contribute more. So let us look at the large powers, the coefficients of the large powers of xi. Now so the relation between the coefficients is given by this. So let us see what happens when we take the limit of s being very large. In the limit s being very large, what we see is that this n is a fixed number which can be forgotten when s is very large. Similarly, 1 can be forgotten, and this 2 here can be forgotten. So what we get when s is very large is as follows. So for large s, Cs plus 2 by Cs is equal to 2 by s. Let me show you the relation once again so that you are convinced. So if you look at this, for large s, the Cs plus 2 by Cs is equal to 2 by s. The s here and the s here cancel out. Okay. So now we have obtained this relation between the coefficients at large s. Now or which is also the relation between the a's, as plus 2 and as. Okay. Now let us look at the series expansion of this function, e to the power xi squared. So if I do a series expansion of this function, I find what I get is that this is equal to 1 plus xi square plus xi to the power of 4 by factorial 2, etc., which is equal to the sum of from m equal to 0 to infinity xi to the power of 2m by m factorial. Or I can write this as defining s to be m by 2, then I have s is equal to 0 to infinity xi to the power of, this is okay. So xi to the power of s is 2m divided by 2s factorial. S is only even. So this is only even now. S is m plus 2, 2m, sorry, S is m 2m. So if I use S to be 2m, so S is now only even, then this is xi to the power of S, S by 2 factorial, right. So this is S by 2 factorial. Now let us look at the ratio of the coefficients of Cs plus 2. So for this series, the ratio of the coefficients, so Cs plus 2 is equal to by Cs is equal to how much? This is equal to 1 by S plus 2 by 2 factorial divided by 1 by S by 2 factorial, and what we have is that we have a factor of 1 by S plus 1 by 2 left after we cancel out these two. So this is, and for large S this is just equal to 2 by S for large S. Okay. So what we find is that if we do a Taylor expansion of this, the coefficients satisfy this same relation for large S. So we are led to the conclusion that the V1s which we had, V1 xi, yes, S plus 2, oh sorry, this should be S plus 2. So S plus 2 by 2, which for large S is just S by 2. Okay. So we are led to the conclusion that V of xi for large xi behaves as proportional to e to the power xi square by 2. Similarly, V 2 xi behaves as xi into e to the power xi square by 2. So for large xi, we are led to the conclusion that, no, sorry, there should be no power by 2 here. So it is just e to the power. So this is just e to the power xi square, and this is xi into e to the power xi square. We had looked at the Taylor coefficients of these, right? So these blow up as xi increases, and it blows up as e to the power xi square. Now let us go back to our original expression for the wave function psi. So if we put back those two forms into the wave function, what we get is that for large xi, this behaves as a e to the power xi square plus b xi e to the power of xi square e to the power minus xi square by 2 for large xi. So we find that for large xi, the wave function behaves like this. Now, so let us look at the xi going to very large infinity limit. So as xi goes to infinity, we find that this function blows up, this function blows up. There is no choice of coefficients a or b by which we can make these two cancel. So we are led to the conclusion that psi itself blows up as xi goes to infinity. The resultant product actually blows up when as xi goes to infinity. Now, we don't want this kind of a behavior. We are studying a simple harmonic oscillator, and we want to look at particles which are there within a certain region. We don't want to study particles which are located at infinity. we would like to study particles which are localized in a certain region and not at infinity. If the probability blows up, if the wave function blows up at infinity, then it means that the probability of finding the particle is largest at some very distant place. We don't want such a situation. We want a situation where the particle is known to be within some region and not somewhere, some distant place. So we don't want this kind of a behavior for our wave function. So how can we avoid such a behavior? The only way you can avoid such a behavior is as follows. Suppose n is an integer. Let us look at the recursion relation again. Suppose n is an integer. If n is an integer, let us say it is some integer, let us say it is 0. n is 0. So if n is 0, then psi C0 is, suppose we choose the value of C0 to be something arbitrary, and we want to use this to calculate C2. So if we want to use this to calculate C2, then we will find that C2 using this recursion relation, C2 will be equal to 2. So C2 will be obtained by setting S equal to 0. If we set S equal to 0, we find that this n is 0, S is 0. So this numerator over here on the right hand side is 0, which means that C2 is also 0, is equal to 0 minus 0 C0 by 1 into 2, which is 0. So if n is 0, so if n is 0, then C2 is equal to 0, C4 is equal to 0, all the others are 0. So suppose we choose C0 is 1 or some number and C1 to be 0, then we find that V1, so we are going to choose, this whole thing is 0. So we have a situation where C1 is some number, C2 is equal to 0, C1 is equal to 0. This implies that all the other coefficients are 0, because so we only have C0 and C1 is equal to 0. So all the odd are 0 because C1 is 0 and all the odd ones follow from C1. All the even ones beyond C2 and C2 included are all 0. So we are left with just V1 xi is equal to some constant C0. Similarly, if we choose n equal to, let us say 1, if n is equal to 1, then we find that we can, so we have a C1, n equal to 1, suppose we have n equal to 1, and we want to relate C3 to C1. So we are starting with a C1 and we want to calculate C3. So C3, so to get 3 over here, S plus 2 should be equal to 3. So S should be equal to 1. If S is equal to 1, n is also equal to 1, then 1 minus 1 is 0. So if, so what we find, let us calculate C3. So C3 is C2 plus 1, 1 plus 2, which is equal to 2 into 1 minus 1 into C1 by S is 1. So we have 2 into 3, which is 0. So if n is equal to 1 and C0 is 0 and we just have a C1 which is non-zero, then we find that all the even ones are 0 because they follow from C0. All the odd ones, C3, C5, etc. are all 0. It follows from the recursion relation. So let me just summarize the whole effect. If n is an integer, let us say it is an odd integer, or even let us say it's an even integer to start with. Suppose n is equal to 2. If n is equal to 2, then what happens? We can, okay, let us just work out n is equal to 2, and that will explain everything very clearly. So for n equal to 2, let us we start with C0 and n is equal to 2. So for n is equal to 2, we have C0 and then we have 2 into, so n is 2, and we want to calculate C2 from this. So in order to calculate C2, we should set S equal to 0. So let us set S equal to 0 in this equation. So if we set S equal to 0 here, what do we get? We get C2 is equal to 0 minus 2 divided by 3. No, sorry, S is equal to 0 will be 1 into 2. So this is equal to minus 2 C0. Let us now calculate C4. Once we know this, we can calculate C4. So C4 is obtained by setting S equal to 2. So if you set S equal to 2, this will be 2 minus 2 into C2 divided by 3 into 4, which is 0. So all the other higher ones are 0. So if we start with C1 equal to 0, C0 not equal to 0, and we have n equal to 2, we find that we can go up to from C0 and C2. C4, C6, etc. are all equal to 0. So if n is an integer, suppose n is an odd integer, then we find that we will get a series where the highest of odd powers of xi with the highest power being n. Similarly, if n is an even integer, then we will get a series of powers of xi where with only even powers of xi where n is the highest power. Okay. So if n is an integer, the series stops at xi to the power n, and it doesn't blow up as xi goes to, it doesn't blow up as fast as e to the power minus xi square by 2 falls off. It doesn't blow up so fast, and we have a well defined wave function. So we are led to the conclusion that n has to be integers. So if we want well defined eigenfunctions, if you want the wave function to be well behaved at infinity, then n has to be an integer. So if n is an integer, this puts restrictions on the eigenvalues of energy which are allowed also. So if n is an integer, then what does it tell us about the energy? So let us go back to the relation between the energy and n. The relation between the energy and n was E was equal to h cross omega n plus half. This was the relation between the energy and n, or we can put a subscript n here to indicate that it is the energy corresponding to the nth n value n, and n can take values 0, 1, 2, 3, 4, etc. If n is not an integer, the wave function is ill behaved, such values are ruled out. So the only allowed eigenvalues, the restriction comes from the boundary condition that psi must disappear at infinity, and the only allowed eigenvalues correspond to of energy are these where n is an integer. So what are the properties of this? Let us first look at this. So this is called the spectrum, the energy spectrum of the simple harmonic oscillator. Why is it called the energy spectrum? Suppose I have a particle moving in some simple harmonic oscillator potential. I make a measurement of the energy. Then I have told you that the outcome of the experiment is going to be one of the eigenvalues of the Hamiltonian. So if I make a measurement of energy for a particle moving in a simple harmonic oscillator, I am going to get one of these energies where n is equal to 0, 1, 2, 3, 4, 5, etc. So this is called the energy spectrum. A measurement of energy is going to always reveal one of these values. Okay. The second point to note is that the lowest energy, so the lowest energy which you can have is n equal to 0. This is called the ground state. And the ground state has got energy E naught is equal to half h cross omega. So this is the lowest energy a simple harmonic, a particle in a simple harmonic oscillator potential can have. It cannot have an energy lower than this. There is no energy eigenvalue lower than this value half h cross omega. You cannot have a wave function corresponding to a particle with 0 energy. There is no wave function. Why is it so? If there was a state corresponding to a particle with 0 energy, it would imply, so if there was a state with energy equal to 0, this would imply both x equal to 0, p equal to 0, because the energy is p square by 2m plus half omega square m square x squared. So if the energy were 0, it would imply that both x is equal to 0, p is equal to 0. Well, then if I knew that the energy were 0, I would know with absolute precision the value of x and p if I had a situation where the energy could be 0. But we have seen that you cannot determine both x and p with arbitrary precision. There has to be some uncertainty between the two. So this is consistent. We find that E naught, this minimum energy which is there, is consistent with the uncertainty principle, and an energy E equal to 0 is not. Okay, this is why we don't have, this is not consistent with the uncertainty relation. Not with uncertainty relation. So this is one more feature. Let us look at another feature of the, so let us then now draw the eigenvalue spectrum. So the eigenvalue spectrum looks like this. So I have the lowest energy, this I am plotting E here, and other different allowed values of energy. So this is n equal to 0. Then I have n equal to 1, n equal to 2, n equal to 3, etc. So this goes on. So we have a discrete spectrum. The spectrum has got infinite number of energy levels, each separated by h cross omega. They are equally spaced and infinite. So if in any situation in nature one finds energy levels which are equally spaced and many of them, then it indicates that the situation, the particle which is generating the spectrum, can be described by a simple harmonic oscillator kind of motion. Such a situation, this kind of spectra is seen quite often in many situations. Like, for example, I told you the oscillations of an atom or molecule in a solid can be described by a simple harmonic oscillator, and the spectrum there, spectrum of energy, has got this kind of a distribution. They are equally spaced with some fixed spacing. Okay, so this is the energy spectrum. Let us next look at the behavior of the wave functions corresponding to different energy values. So let us look at the behavior of the wave function. So the simplest one is n equal to 0. So this is the simplest case which we have, and I have told you for n equal to 0 we have psi as a function of xi. This is equal to, the only coefficient which is there is C0, and so we have just some coefficient C0 into e to the power of minus xi square by 2. So this is the 0th, the wave function corresponding to the 0th, the ground state of the wave function of the simple harmonic oscillator. So this is called the ground state wave function. Psi 0, n equal to the value of the n is denoted here in the denominator. So this is the ground state wave function. Let us also look at n equal to 1. So psi 1 xi is equal to C1 into xi into e to the power minus xi square by 2. So we have the two this is the first, this is called the first excited state of the simple harmonic. This is the first, this is some kind of nomenclature, first excited state, because it has got an energy higher than the ground state. We can also write down the xi n equal to 2 wave function. So the n equal to 2 wave function is xi 2 psi 2, which is, we had for n equal to 2 we had calculated C2. So for n equal to 2 we had found that C2 is equal to minus 2 C0. So we can write this as C0 into 1 minus 2 xi square e to the power minus xi square by 2. So this is the second excited state. So let me show you, instead of plotting them, let me just graphically show you these functions on the computer screen. So let me just graphically plot these functions. So plot exponential minus x into x by 2. So this is the Gaussian function. This is the ground state. This is what the ground state of the simple harmonic oscillator looks like. It is just a plain old Gaussian with which we are familiar. Now let me also plot the first excited state, which is okay, I will show it just now, 1 second. So can you see it now? There are two. Okay, they will, I think they will okay, let me plot all three of them, and then we shall discuss them. In the meantime, they should Okay, so I shall continue in the next class with I shall show you these three functions.